Hi, GopherCon. Everybody good? Cool. It's great to see so many people here. My name is David Symonds. I work at Google on the Go team, and specifically I take care of the Go Runtime for App Engine, along with a few other people. And what I want to do today is do a bit of a retrospective. So I don't want to come up here to sell you on how good it is, even though I will tell you briefly how good it is on the way through. But I want to kind of look back on the last few years, tell you about some of the interesting things that we've found as we've been developing this Runtime for App Engine. Some interesting things that we found different from other languages, other runtimes. I want to just give you a bit of a peek behind one of the curtains that we've got to show you how we did something. And then just go through a couple of things that we'd do differently if we could, travel in time. So I'm sure you all know that Go is pretty awesome. Don't need to tell you guys that. App Engine is Google's cloud product, also known as something that runs on servers. It gives you an auto-scaling, low-maintenance platform as a service. So what that actually means is that you write a web app with Go, you give us the code, we build it, we run it, we get woken up when it goes down, you don't have to. When a farmer in Atlanta cuts through a fiber line, we take care of switching over to a different data center. We take care of all that operational stuff for you. So you can just write your code, deploy it to App Engine, and we take care of the rest. It also provides a bunch of services, so you don't need to run your own memcache, you don't need to worry about setting up your own storage systems, you don't need to worry about how to send email without getting blacklisted from various places and so on. So we take care of that kind of stuff as well. And Go is the most efficient runtime on App Engine. It starts really fast, it runs really fast, and it uses very little RAM. It also powers several critical pieces of internet infrastructure, such as the Google Standard Tracker, Secret, the iPhone app for gossiping amongst tech workers, and GoRead.io, that's a very popular Google Reader replacement. The interesting thing to note about all these, though, is that they're all built by very small teams, 1, 2, 3 people, and they're all run by very small teams. They don't have to employ a bunch of sysadmins to carry the pages and get woken up at night. They can just write their code, deploy it, and then sleep well at night. So where Go fits into, where Go on App Engine fits into Go's history, it started pretty early on. Go was open source and announced to the world late in 2009. Only a little after a year later, we started working on it. And Go 1, the stable release, arrived about a year after that. You'll notice there's a good overlap where we didn't have a stable version of Go to work with. That made things certainly interesting when we first started building it. The make files and calling out to 6G and 6L were the standard way of building Go libraries and Go programs. The Go tool didn't exist. And package layout was kind of understood, but not solidly baked in and understood like it is today for third-party packages especially. So there was a lot that we were doing and learning and kind of running in place. And sometimes when I talk to people and say, I work on Go on App Engine, I said, that's like a weekend project or something. People kind of underestimate how much is involved in building a runtime for a platform as a service. There's API packages to build and APIs to design, which turns out to be really, really hard. There's app server integration. So the way App Engine works is that you have a bunch of app servers, and each of those runs lots of instances of all kinds of different people's apps. You have to make sure that they stay isolated, so one person's Santa tracker is not interfering with Secret and spilling secrets of Santa or whatever it is. So you've got to fit into that system properly. You've got to build an SDK because developers kind of want to work locally, not just in the cloud or on a server. And then there's, of course, documentation to do that unfortunately gets left far too late and is always a little bit behind. So we were doing all this stuff with a very, very small team. All while the language was still evolving, we found some interesting compiler bugs in the process as well. The standard library was evolving, so this was back when os.error was a thing. Who here remembers os.error? Wow, so the proportion is shrinking. That was like maybe a quarter of the room. So we were kind of building all this stuff, trying to maintain backward compatibility as well, because we wanted to be able to tell people, hey, give us your code and we'll run it. But then we didn't want, a couple months later, oh yeah, the Go standard library changed, we're not running your app anymore. So we were kind of trying to figure out what that meant as well. And I want to make sure that everyone knows it was a team effort. There was quite a lot of people who had specialties. I'm certainly not an expert in all the things that were involved. So we did rely on people everywhere from modified runtime up through the compilers and linkers, through various libraries that needed work done on them, SDK integration and so on. There was lots to do. So I want to spend a couple minutes just chatting about some interesting differences that we had from the other runtimes. So who here is familiar with App Engine? Okay, leave your hand up if you've used App Engine at all. Okay, leave your hand up if you've used Go on App Engine. Oh, okay, cool. That's pretty good. So before Go came along, there were two other runtimes on App Engine that all those people that put their hand up at one point know about. Python 2.5 was the first one that was launched in 2008. The Java runtime was launched a year or two later, and then Go came along. And we did several things differently for various reasons in Go, and I want to go through a few of those because they really highlight some of the things that are interesting and different about Go, that some of them we knew in advance, and some of them we kind of discovered as we went through that the existing models didn't fit. So the first one, and probably the most controversial one even amongst us, even amongst the Go team, was using an explicit context. So the way that API calls work from your app is that they need to do effectively a little RPC back to the app server that then checks that the app is allowed to use that service or whatever it is, hasn't gone over its quota, and then the app server takes care of making the API call, for instance. And that's for lots of different reasons. The main reason is because random people give us code and we're running it on Google servers. We can't necessarily trust all that code to be well behaved. That's a unique cloud thing. So we need to protect apps. We need to protect Google's infrastructure from apps. We need to protect apps from other apps. And we need to sometimes protect apps from themselves. So in case you write some bad code, we don't want you to suddenly run up a $1,000 credit card bill overnight because you didn't notice what was going on. So API calls need to ship along a security ticket, which is a fancy name for an opaque string, or roughly a nonce, for every running request. So as a request comes into an app, the app server assigns it a unique randomly generated string and passes on to the app. And then it expects the app, for every API call it makes to the app server, to tell about what that ticket was to authenticate it. So I mentioned this is used for quotas. So depending on the request, you might be able to use more quota than others. More particularly, some authentication restrictions come in here. So for example, the way that you can send email from App Engine, the sender of the email can be one of two things. It can be an application admin, or it can be the currently logged in user. So you could write an app that allows a user to send email. But we don't want apps to be able to send email as anybody. So by using a security ticket, we kind of link the incoming request that we've authenticated as a particular user with, say, a request to send mail, and we can identify, yep, that logged in user is listed as the sender of this email. I'll let it go through, otherwise we'll knock it back. It also does association of the logging. So in the admin console for your app, you can go through and see all the requests that have come in, and then for each request, you can see all the log messages for that line. So a security ticket associates the log messages as they happen with the particular request that was being processed at the time. So the way that this security ticket works in the other runtimes is that Python doesn't serve concurrent requests, at least Python 2.5. So it just uses global state. So when it's serving a request, it just sets the security ticket in a global variable, and then every time it makes an API call, it just pulls it out of that. So that's nice and simple for Python. Java uses thread local storage. So as long as you're implicitly on the right thread, it'll find the right security ticket and send that along. Go, however, is both concurrent and avoids thread local storage. So we had a bit of conundrum how we were going to associate any bit of code that wants to do an API call with the request that is being processed. The way we did this was with this context interface that have different implementations in dev and prod for various reasons. But then the way this works is that your HTTP handler can call appengine.newContext, pass the request, and it gets back this context type that it can just pass around to any of its API calls. So this is pretty controversial because it's kind of nice not to have to, when you're writing code, to do net.dial, and then you can just give it an address. You don't have to say, oh yeah, and I'm doing it on behalf of this other thing. So it's kind of a little cumbersome at times, but it turns out to have some really nice artifacts about it, some really nice unanticipated effects that we found as we went through. First is that it allows us to implement timeouts very naturally. So API calls will have a default timeout, but often you want to change that timeout. You might be fetching some remote resource, and instead of waiting for 10 seconds, you might realize it's a slow resource, and you might want to wait for 30 seconds. The way we implemented overriding timeouts was providing you a function where you give it a context and a new timeout, and it gives you back a new wrapped context. So any API call that tries to use that context will have its bits twiddled underneath the hood and then have that new timeout. This means that we didn't have to go through and edit any of our APIs to support timeouts. So application user code can use exactly the same APIs to send mail, to fetch URLs and so on. And then if they want to customize the timeout, they just call this timeout function, get back a new context, and anywhere that new context is used, you've got a modified timeout. As opposed to Python, the Python programmers had to go through and add keyword arguments to all their APIs to be able to override timeouts. So in actual fact, being forced to pass around this explicit context made it really easy to avoid modifying the API in different ways. Another way this helped was when we went to implement namespaces. And this is called multi-tenancy. You can imagine you're running an app that services different companies' data, and you want to keep the company's data nicely isolated. This allows you to tag things with a string namespace, and then whenever you're accessing the data store to fetch some data, you pass in that namespace, and you make sure that you're accessing company A's data when you've got a company A request, and you're not going to accidentally get company B's data. And the way this works in Python is that they set a global variable. So as a request comes in, it works out, oh, I'm now in this namespace, I'll set this global variable, and then anything else that it does will be in that namespace. That works fine if you don't have concurrent requests, but it doesn't work well in Go. But again, we could reuse the same idea that we used for timeouts. We can just wrap this interface a second time, and then when an API call is trying to use that context, it'll just twiddle the right bits under the hood, all transparent to the API, and then it makes it very impossible to accidentally access the wrong type of data. The third thing is that transactions worked exactly the same. So the data store allows you to do a certain limited type of transactions, and the way that works is that you invoke a function and give it a callback, a closure, and then it will run that function and pass it a new context that's, again, wrapped. Then any API calls you do in that will have its bits twiddled underneath the hood, automatically applying all the transactional information, and we don't have to modify our APIs again. So we're able to support these three major features across all the APIs without having to modify any of the APIs. And this was a nice feature where Go's interface design supported the orthogonality of this kind of API design. Second thing I wanted to talk about is language primitives. Unlike in Python and Java, Go has some fantastic primitives for supporting concurrency. So you can be running multiple things at a time. Back when App Engine first launched, the model was very simple. You've got a Python script, and it might be running a guest book, and a request comes in, and you go and fetch data that you need to render the guest book page. You get it back, you render your template, and you return it to the user. But then people realized that they wanted to run more complicated apps on App Engine, and they wanted to do multiple things at a time, and they didn't want to wait 30 seconds to process a request. So that means they need to run multiple API calls at a time. Python and Java needed to have separate async APIs for these things to support this. So just as they had to go through and add keyword arguments to support timeouts, they had to change globals for namespaces and so on, they had to provide asynchronous versions that would give you a callback to wait on after you've set things up. So they ended up having to expand their API service quite a lot. Go, on the other hand, has the Go keyword, and then we were done. So again, we didn't have to change our APIs, and that was pretty good. But the thing that always got me about this, that I didn't realize until coming through this and designing the APIs and realizing that we could do all this, looking back on talking to lots of people about Go, learning Go, and complaining about Go, whinging about Go, and writing to the mailing list complaining about various features of Go, is that there's a lot of complaints about what Go lacks, but there's not a compensating volume of what Go has. And I think we get used to seeing these features and go, oh, that's nice. I think I can see how to use that. But then we don't make a big fuss about it. We just get on and use it. But if something's lacking there, we tend to yell about it. And in this case, being able to design APIs in this kind of orthogonal, simple way where you have language primitives to help you out is pretty not as well understood or appreciated as I think it should be, because we didn't need to go and add asynchronous versions of the task queue API, asynchronous versions of the mail API, all these things, and you don't have to wait for us to do a whole lot of work before you can combine these things together. You've got the language and you can combine them together yourself. Go also encourages use of plain data structures. It's fairly an understated language. It doesn't encourage you to build large data hierarchies or type hierarchies. The Python and Java data store interfaces kind of expect you to subclass a certain classes they provide so you can access data and so on. But the Go style of using plain data means that you don't have to go out of your way to specially make a struct for data store, or a special struct for JSON, or a special struct for XML. As long as you write it carefully enough, you can use it as a simple struct in all three. And I think this is another less understood part and less appreciated part of Go, where it encourages you to do the basic stuff and keep things simple, but then it has great flow-on effects because you can reuse things a lot more easily. The third difference I wanted to just chat about briefly, and this isn't intended to be a bit of a Python and Java bashing session, but it is a notable difference that we've found and again and again, is that Go treats things from a bit of a fresh perspective, and it wants to see things with fresh eyes, perhaps older eyes, back from when things were called servers rather than cloud. But as a result, it's kind of seemingly very different than other languages. So it's not different like Haskell or ML, but it's different enough that it often doesn't fit into the molds that people have already settled on. So for example, in the internal App Engine infrastructure world, there's a bunch of internals and documents and structures in place that assumed a Python-like language where you had an interpreter that you could start generically, or a JVM that you could start generically, and then when you're ready to, you could add on the particular piece of a particular app. And these were kind of reasonable assumptions to make about several languages, but they weren't true for Go. So we had a good wrestle with trying to fit Go into that system, that kind of infrastructure. We had to kind of make some changes there to support Go. So one thing that they had, for example, when you upload your app to App Engine, it can do a pre-compilation step. So for Python, this would be parsing in the .py files, building up the AST and so on. So then when you're actually running your app, you don't have to go through that step. You can just save that intermediate state away. But for Python and Java, that step is completely optional. If it fails, if it times out, if it takes too long, then your app can still work. So the upload process assumed, well, if it fails, it fails. We'll print a warning message. Your app might not be quite as great as it should be, but it'll still work. For Go, optional compilation is not so optional. So we had to go through and find all the places that it assumed that the app being uploaded could be compiled. It'd be nice if it compiled, but we had to kind of nail those down and make things not so optional. And instance scheduling, I mentioned that Python and Java kind of assume that you can start up a generic thing and then quickly load on your app on top of that. Go doesn't have that big thing to load up, and so we had to tweak a lot of the scheduling to remove the assumptions or to allow tuning so that things didn't spend a lot of time when they didn't need to. So here is a promised peek behind the curtain. This isn't super secret, but I believe this hasn't been talked about in public before. This is a look of how we keep Go on App Engine safe. By safe, I mean that Go is a memory safe language, but its implementation is not memory safe. So for example, you've got a bunch of data structures in the language that are implemented in the standard implementation using a multi-word structure. And you can race with multiple Go routines running at once on different threads, and you actually get inconsistent, according to language spec, behavior on that. But part of the security story for Go on App Engine was that Go was a memory-safe language. And coming after Python and Java, which are also safe in that sense, it was a pretty key part, and we needed to be able to guarantee that some random person's code running on App Engine wouldn't attack Google services from the inside, so to speak. So to keep that memory safety in place, we need to keep the Go runtime, and runtime here meaning the stuff that implements maps and channels and Go routine scheduling and so on. We need to keep that single-threaded. The important point here, though, is that this preserves concurrency. So we are not ripping out the concurrency of Go. And this is where, for example, the difference between concurrency and parallelism matters, because your app can still be just as concurrent as running on your own hardware in a completely unrestricted environment. We've just pulled out the parallelism, and in particular the CPU parallelism. So a web app on Go on App Engine can only run on a single CPU thread at a time. So while it's doing other things, it can switch to running a different Go routine, but it can't have two Go routines running on two different threads at the same time, potentially dueling over a piece of data. And this preserves our memory safety, preserves concurrency, but just makes it safe. So the steps that we do here, I'll go over this briefly because it does get rather technical, but come and chat to me later if you want more details. We disallow importing a couple of packages that would provide loopholes or escape holes. We want to make sure that interactions with the outside world are mediated, so you can't just make random network connections to random hosts. There's a sockets API that allows you to do that, but that's carefully controlled and filtered and quoted by the app server. So what we do is that we swap out the runtime, and particularly the Go routine scheduling, for a discrete event simulation style model. Now it's discrete event simulation-ish. If you've ever done these kind of simulations, you know that they don't kind of run in real time, but if you've used Go on App Engine, you know that if you do a sleep, it actually sleeps for the right amount of time. So what we do is that we break events down into two categories. They're either operations on file descriptors, which can be anything. It could be waiting for network traffic to come in. It could be waiting for an API call to return, a file to be read, or things that are waiting on a timeout, whether they're sleeping, whether they're doing an action with a timeout, whatever it is. And this is enough to divide the complete world and capture everything that could happen as far as the schedule is concerned, and capture that as an event model. And then we build an event loop on top of that based on container heap that just makes a priority queue. So we've got a queue for all the file descriptors that we're waiting on, and then we've got a queue for things that we're waiting on to time out or to sleep. That's enough to run the complete Go scheduler from under the hood. Then we plug this into a heavily modified proc.c, and then anytime it would consider starting a new thread, instead of doing that, it just doesn't, and then adds any information to this event loop. So it realizes, oh, I'm about to do a system call that will block. I won't start a new thread. I will instead add this Go routine, add a record of this file descriptor to this heap-based event loop, and then I'll just switch to something else. So all of this is kept in a single thread, and then I'll just switch between things as they're ready. This is just a much more complicated version of what the playground runs. This blog post is a good overview of some of the details. There's a lot more going on in App Engine land because it's got to deal with actual file descriptors and so on. This did lead to an interesting bug that I wanted to describe for you with some of the time that I've got left. So Cloud SQL is the Google Cloud Platform's offering of MySQL in the cloud or MySQL on a server that you don't run. And the way that this works from an App Engine app's point of view is that you try to connect to some MySQL database, and it will just give you back a file descriptor. And on that file descriptor, you talk to MySQL wire protocol. So you can use whatever MySQL driver you want. And this keeps it very simple. There's very little for us to implement. We've just got to go fetch the right file descriptor and then give it to the app. And then it's up to the app whether they use person A or person B's MySQL driver. It's up to them. And we launched this a number of months ago, I think 6 months ago or something, and everybody was quite happy with it. It worked fine first out of the gate. It was very simple. Most of the problem was with getting the MySQL drivers to do the right thing with it. And people were happily using it until about a month ago when we got a bug report saying that it looks like my app instances can't do anything else at the same time as doing a Cloud SQL query. And that was a bit weird for us. And they gave us a reproduction, including apparently MySQL allows you to do a select sleep. I don't know why you'd want that, but you can do that. And they demonstrated you do a select sleep 30, it'll sleep for 30 seconds on that network request, and then your instance is unresponsive completely for all that time. We dug into it, and we found out that the bit of code that was getting that file descriptor for the Cloud SQL interface wasn't adding that file descriptor to the event loop. So I was doing raw system calls over that. So that didn't violate any of the safety, but it meant when you started doing a blocking system call on that file descriptor, it wasn't passing on to any of our other things in the event loop. So it just completely blocked your instance during that time. And it was interesting because nobody really mentioned it before this guy noticed it and dug into it and then came up with this reproduction using sleep. But it was one of these kind of bugs that was kind of fairly subtle, interesting to diagnose, and then a really easy fix. It was like 2 lines to change. But it was an interesting thing that we were kind of just assuming that the Go runtime was handling everything, and in this case it wasn't. So a couple of things that we'd do differently if we could, but we can't because we treat backward compatibility seriously. I mentioned kind of early on that we designed a lot of this in the early days before the Go tool, before Go 1, back in the days of os.error, with men walk with dinosaurs. And we didn't have a notion for how an app would look like. You present us with a bunch of Go source code. Do you have to give us an XML file to say how it's laid out? Do you have to, all this kind of stuff was still not settled and not understood for Go itself. So we were kind of trying to make stuff up as we went. Happily, we came up with something very similar to how GoPath and the Go tool works now, where you get packages based on the directory layout. But we needed some way to get the App Engine packages for App Engine/mail or App Engine/data store in front of the application so it could be built against. And one kind of misstep that we did that if we were kind of a year later might not have done was we weren't using any workspaces. We kind of made those App Engine packages look like they were part of the standard library. This kind of caused us a few problems. It made it simple because we could just, as you uploaded your app, it just gets built against the standard library and hey presto, there's the App Engine packages. But it meant that you try to build your code that might use App Engine stuff, and how do you run tests against it? You use the regular Go tool now, but those packages aren't in the standard library. How do I even build this code? So we'd kind of change this to use regular Go gettable packages in the future. Channels in the data store probably load saver. Sorry if you've had to deal with that. That was my fault. I thought it would be much more useful to preserve how much memory we're using as you preserve. So probably load saver is kind of like an adapter to when you get an entity out of the data store to be able to turn it into some Go type. And the default setup is just use the struct property load saver. So you have a struct and all your fields are named in the right way and it'll just plumb it all through. But if you want some other general way, say storing into maps or mutating the data as you fill in your structure, we have this interface that I thought passing through the properties one at a time through a channel would be good. It turns out it's just a pain in the neck. We can't change this now, but we are changing it in the equivalent in the search package and in what I'm about to briefly mention next. Managed VMs is the next evolution of App Engine. So App Engine is great because you can upload your app and we take care of running it. You can go to sleep. Google SREs will be woken up in the middle of the night if something goes wrong. So it's great from that management point of view, but as a trade-off, it means that you have to restrict what your apps can do. So you can't import syscall or unsafe. You can't write racy code that uses multiple threads. You can't do arbitrary network operations and so on. And that's kind of a pain in the neck for lots of use cases. So Managed VMs is about trying to shed all those and move the security barrier back from around the app itself to the machine, in this case a virtual machine. So Managed VMs is kind of App Engine on Compute Engine. And there's a workshop on Saturday that's going to go through this in a bit more detail, and you'll have an opportunity to play with this, get some free credit to try it out. As well as getting more restrictions, you get high performance because you're not CPU locked, because you're not trying to share a single machine with a few hundred other applications all running at the same time. But this gives us a little bit of a break in our backward incompatibility promise. So we are going to make a few small backward incompatible changes, like what I mentioned on the previous slide. The API packages are all things that you just go get, and so on. So just a few links. I'm sure you've all seen the top one. The second one is the starting point for Go on App Engine if you want to explore it a little bit. Don't forget to come to Saturday's workshop. It should be a lot of fun. And my time is well and truly over. So thank you very much for listening.